Hello, I'm Deborah Beck, and I will begin my presentation on centrality-based visualization of small word graphs. My presentation contents are as follows. I will start with introduction. First, force-directed layout algorithms, which are traditionally used methods for drawing graphs, are straightforward to implement and provide satisfactory results for many different types of networks. And it's possible to create node links layouts of graphs of tens of thousands of nodes in limited time. However, for dense graphs or sparse graphs with small diameter, images are often not informative. Because of the small average path lengths between nodes, node link visualizations make uniform clump of nodes and tangles on graph, and it makes it hard to identify structural features and overlapping edges, which make finding paths becomes impossible. The reason of overlap is force-directed layout algorithm tries to keep all connected nodes close to each other. In practice, a more informative layout can be achieved if we eliminate some of the edges before applying a layout algorithm. To do so, we can use edge weights, but dense structures are usually formed by higher weight edges, and many real-world graphs are unweighted. So using edge weights may not be a good approach. Therefore, another edge selection algorithm is needed. In this study, three criterions are proposed as ideal criteria for edge selection algorithms. First, it should not produce disconnected components if the original input graph was connected. Second, it should strike a balance between reducing the number of edges such that the resulting graph is easier to visualize, while maintaining as many of the original edges as possible. Third, it should leave the clustering structure in the original graph intact. If two nodes are in the same structural cluster, they should be positioned closely together in the reduced graph. In this paper, edge-betweenness centrality is presented as an algorithm that satisfies these criteria. By using edge-betweenness centrality, we can extract sparse structures from the graph that capture the overall structure well and conform to the criteria above. Before edge-betweenness centrality, there were several existing approaches to handling the problems. It was adjacency matrix representation, computing a clustering on the input graph and then rendering this clustered graph structure, and extracting a subset of edges that are a good approximation of the graph structure, and pathfinder networks. Each of these methods has advantages and disadvantages. However, we will not discuss it here now, and I will just explain the new methods done in this study. Let's move on to the approach to explain the main idea behind the paper's method. In undirected graph G, each of the following functions have the following meanings. First, E means edge connecting node X and node Y. W means numerical weight of an edge. Length of a path means sum of the weight of edges between two nodes. And shortest path means path with minimal length. Next, Sigma AB denotes the total number of shortest passes between node A and node B. And sigma ABV denotes the number of shortest passes contained node V. Rho ABE denotes the number of shortest passes contained HE. As a result, CV means betweenness centrality of node V, and CE means betweenness centrality of HE. H betweenness captures the connectivity structure of the graph, as edges with high betweenness are present in a large number of shortest passes and can be considered important bridge edges between loosely connected parts of the graph. The main approach and main contribution of this paper rests on following assumptions. If edges with high betweenness serve as bridge edges between different clusters, edges with low betweenness will connect nodes that are in the same cluster. Our approach can be divided into two phases. The first step is to reduce the amount of edges that are fed into the force-directed layout algorithm. And the second is add the removed edges back into the layout. As a first test of the hypothesis that removing high betweenness edges would yield a structurally meaningful abstraction, we decided to generate a minimum spanning tree for a real-world example. In the figure 2, A shows the result after a standard force-directed layout, and it succeeds in keeping artists with identical movements somewhat together, but obscures connectivity information. B shows the result after a force-directed layout using a lean log model, and it manages to roughly group nodes in clusters, although it is not always clear why some nodes are clustered together and other groups are split apart. Regardless, the large amount of edges in both these representations make them hard to read. And last, C shows the result after computing a minimum edge centrality spanning tree and performing a force-directed layout. And it proves a surprisingly good match to the inherent clustering structure present in the graph. Most movements show up as connected pieces of a single color, and the overall ordering of the nodes reflects the ordering from classical to modern artists. This rudimentary view of the graph is already helpful. Although it does not allow us to spot the cluster borders, we can use it to gauge how a particular attribute is distributed over the structure of the graph, and if it might be a good indicator to predict clusters. Generally speaking, if connected branches in the tree share the same value for an attribute, this attribute will be correlated with the structure. Although the minimum spanning tree seems to reflect the cluster structure well, it does not meet the requirement 2 in section 1, that is, it throws away more edges than is necessary. There is no reason why we cannot add more edges to a minimum betweenness spanning tree, but adding edges until our graph has the desired density can lead to the same drawback as adding edges with low weight in weighted graphs. So we use a simple, greedy heuristic that inspects edges in order of non-decreasing betweenness and adds them to the spanning tree if their addition does not invalidate planarity, which is leading to a worst case of complexity. Since we add edges in order of non-decreasing betweenness, most edges that are added are cluster edges and they connect nodes that will not be far apart in the spanning tree. This means that the structure of our planarized graph will roughly correspond to the structure of the minimum spanning tree, and consequently the clustering structure of our original graph. In terms of information content, the planarization procedure has added 81% of edges back in for this particular graph. In a way, this planar view gives us a good overview of the local interaction in the graph and how different tightly connected groups of nodes are positioned relative to one another. However, in many cases, the user will be interested in edges connecting different clusters of nodes. Ironically, it is precisely these high betweenness edges we have left out when creating our planar version. So, in the next section, we add back the rest of the edges to the visualization. As mentioned earlier, we want to ensure that edges connecting nodes in different graph clusters remain visible in our final visualization. But adding all of the remaining edges could lead to a messy representation in which paths are hard to discern. So we decided to use the edge betweenness values that we computed to choose the most informational non-cluster edges. And we decided to render the remaining edges as curved arcs overlaid on the planar layout generated in the previous step. We choose arcs because this makes the distinction between edges connecting clusters and edges connecting nodes in the same cluster clearer, while at the same time providing a depth cue. I will go beyond major stability part because of lack of time. If you want to know more about this part, please refer to the paper. Instead of trying to visualize small diameter graphs by using a standard force-directed layout method, we opt to extract a sparse version of the global graph structure. By using two low complexity graph algorithms, we created a planar representation of the graph's overall structure, after which non-cluster edges were added back in. In this visualization, we have not used any node attribute information, and the resulting visualization only reflects the structural properties of the graph. Using node attribute information can make it possible to correlate node properties with structural properties. Another tempting approach might be to use the minimum betweenness metric to generate explicit clustering hierarchies on the graph by iteratively merging nodes with lowest betweenness. Here we have used the betweenness metric merely to extract a structure or the ordering in the nodes, not to compute explicit decomposition of the graph. A number of important areas for improvement still remain. One involves the visual representation of the arcs we use to indicate inter-cluster connections. The visual complexity of the overall view might be reduced if we can group arcs that roughly point in the same direction. Finally, as the betweenness matrix is a global graph metric, it is therefore expensive to compute. So other possible metrics that might produce similar results in less time are needed. It's the end of my presentation. Thank you for your listening, and please email me if you have any questions.